So what do I mean by multiscale? Maybe a first note on that. By multiscale, I mean measures and concepts that take into account micro and macro scales explicitly. And this is collaborative work that I've been doing with Miguel Aguilera, so one of the organizers as well here during the conference. And I'll give you now a very quick overview of what I'm going to talk about. So first, a little bit on concepts. What is complexity? What is emergence? In that context, I'll go a little bit into theoretical work regarding how to study emergence. I'll introduce two measures: whole parts emergence, which is a measure of emergence, and integrated information, which is a measure of complexity. I'll introduce variational inference, and in that context also present some results. And I'll conclude with conclusions, issues, and a further outlook. Okay, so first of all, complexity. I want to start with a quote from Olaf Spons. So the complexity of a physical system or a dynamical process expresses the degree to which components engage in organized, structured interactions. High complexity is achieved in systems that exhibit a mixture of order and disorder and that have a high capacity to generate emergent phenomena. So there is a lot in there. I want to unpack this a little bit. First of all, what do we mean by organized structured interactions? So by that we mean that the system reveals some non-trivial structure, and we couldn't deduce those structures by studying the laws at the level of the single components. And this also relates to the capacity to generate emergent phenomena. So those emergent phenomena are the result of structured interactions. And we wouldn't be able to predict those by looking at the single components. And then finally, what do we mean by a mixture of order and disorder? So by that, we refer to the components' behavior, the diversity of those behaviors. So if components all behave the same, that is maximum regularity, or all behave randomly, then we probably have no emergent phenomenon to look at. And emergent phenomena are thought to arise, and systems are thought to be complex if they do a little bit of both. You see that here in this graph as well. But it's also important to say that there are various notions of complexity. So another way to think about it is as a choice of explanation, so an explanatory route that we take to make sense of a phenomenon. So this comes from David Krakauer, who has come up with a so-called quartet of disciplinary traits. So a field can be either quantitative, to what extent do we make use of numbers and calculations, or compressive, to what extent can we describe things with short equations, reductionist, to what extent do we need to go down levels to make sense of a phenomenon, and historicist, to what extent do we need to go back in time. And according to Krakauer, complexity science, so the study of complex systems, is quantitative, compressive, and historicist, but importantly not reductionist. Okay, let's get to emergence. I've been already mentioning it. As a working definition, let's say that an emergent property is one that pertains to the whole of a system and not to the single components. So a very trivial example is this dotted circle here, which does emerge from the set of the single points. And a more complex example is this flock of birds, which you see here. It's a very different type of emergence compared to the dotted circle. And you may ask, what's the relation to complexity? Because I've been saying that a feature of complex systems is that they do have emergent properties. So why having a look at emergence more closely if it's already entailed? Already entailed by complexity. And the answer to that is that just as complexity has many features and may ask many questions, so in the same way, we can also ask under what conditions does emergence occur, and to what degree does it manifest itself? So we can ask lots of questions in this context as well. And here, in collaborative work with Fernando Rosas, we've been coming up with something like a conceptual framework to study emergence, where we think that it doesn't come in one shot, so it's a conglomerate of facets, just like complexity. It's rather continuous, so it comes in degrees, rather than it's existent or non-existent. And they may be complementary, so facets may well coexist. And we put a lot of importance on quantifying those facets, currently mostly in information theoretic terms, because we want to make them productive for empirical inquiries. And we want to move away from using emergence in a trivial way. So the dotted circle is a trivial example, or as a placeholder for something we don't understand yet, or as a wild card for claiming that something magical is happening. And one way to ensure this is to put importance on something called supervenience. That means that no change on the macro scale level can occur without changing the micro scale levels as well. And one way to make that sure is to construct the macro variable as a function of the micro variables. Okay, so what can those facets be? Let's get back to the example of a flock of birds. So we can say, for instance, that the macro scale variable is the center of mass, and the micro scale variables are the locations of the single birds. And we can now ask, is the center of mass an emergent macro scale variable? So, for instance, it could be that the macro variable has unique information about itself that we can't find anywhere else. That's something we do call causal emergence. Or it might be that the macro variables don't have anything to add. So all the information is already in the macro variable, so it's causally closed. Or the macro variable has unique information about single components. That's something we do call downward causation. Okay, let me introduce now the measures. So those are the two. We're going to start with whole parts emergence. There are two versions, one based on standard Shannon mutual information and another one much more complicated on partial information decomposition, in short PID, and integrated information decomposition, in short PHI-ID. So those frameworks are quite complicated to understand if you have never heard about them before. But for those who do know those frameworks, a very quick recap. In PID, we decompose the mutual information, so this term here, so the information that two sources have about one target, into redundant, unique, and synergistic information. And in PHI-ID, where we have multiple sources and multiple targets, we decompose that term into 16 different components. And we can systematically depict this in the so-called redundancy lattice, where each node corresponds to one such component, so one of the 16 parts. Okay, now whole parts emergence. Imagine that we have two variables at one time point, those are the sources, and the same two variables at another time point, which are the targets. So whole parts emergence now is defined as the sum of all the components which have synergistic contributions about the evolution of the system. So it's a sum of those four. And this sum further decomposes into downward causation. So here, the sources have synergistic information about a single component, about the future of a single component. And this is the term called causal decoupling, where the sources have synergistic information about the future of the targets also considered together. All right, so you may have noticed that here in PHI-ID-based whole parts emergence, we have no macro variables. So that's because this measure works without it. So here we just look at the synergistic contributions of the system's components. In the Shannon-based version, we would have a macro variable. I will not go into this right now. So there are correspondences in the Shannon-based version. you can have a look at that at another time if that is of interest to you. We're going to get to integrated information now. So there are lots of different versions of integrated information, but they all have one common denominator, which is, so here using the brain as an example, we make a bipartition of the system, and we ask to what extent the sum of those two parts have information compared to the information that the whole system has. So very often integrated information is abbreviated with the Greek letter phi, and here M does refer to one of the two parts. So we do subtract the information that the two parts have from the information that the whole system has. Okay. Now we'll get to the model, variational inference, which originally comes from machine learning to approximate difficult to compute probability densities. But it has also been proposed that the brain does something similar when facing difficult probability distributions. So it's a very simple model, probably the simplest one that one can look at. So we have two latent variables which follow a bivariate Gaussian distribution. We infer those with a mean field distribution. So the off diagonals are 0 here. And we look at the KL divergence between an approximative distribution and the true distribution. And we use gradient descent here on the KL divergence using this update rule. So here C refers to the covariance matrix. And depending on the weighting factor alpha that you see here, it will be closer. It will be either closer to A or to B. So if it's large, it's going to be closer to A, and if it's smaller, it's going to be closer to B. So this gets relevant in a moment. And we have a noisy estimation of the true mean values. This is because we want to have non-zero conditional covariances. I'll get to that in a moment as well. So what did we vary? The covariances between the latent variables, so the off-diagonal elements in A, and the weighting factor alpha. So to what extent the off-diagonals are taken into account in the update equation. So just to remind ourselves, we look at whole parts emergence and integrated information. So here's the formula again, and it further decomposes into those formulae, which you can ignore for now. This is just for those who may be familiar with them. So what can we expect if we vary the covariances and the weightings? So because we have C in the update equation, we in effect vary the correlation between the estimated means. And it's not clear what to expect with respect to integrated information and whole parts emergence, but we should probably see some variation. All right, so let's first look at integrated information. So these are steady state solutions. So we look at the final values that we end up with in the inference. And on the x-axis, you see the correlation. Okay. And each line stands for one different weighting, with the darkest line being the largest weight. So this is just one. And in the other lines, we do take the off-diagonals in the target distribution less into account. So here we can clearly see that with increasing correlation, we have also more integrated information. But with suboptimal inference, that is where the weight is less than 1, for very high correlations, we do get a little decrease here. Okay, this is now phi-ID-based whole parts emergence, where for a weight of 1, we have a steady increase. For other weights, it seems to either increase or just decrease right away. This is phi-ID-based causal decoupling, which just decreases. Downward causation here, which coming from the negative realm increases towards 0. And then finally, double redundancy, which is a key quantity in phi-ID-based whole parts emergence. We have quite a surprising result for any weight, even for the one where we fully consider the covariance in the target distribution. We see a decrease for large correlations. So normally we would expect that it would just increase the redundancy in the system if the correlation is high. All right, so what do we learn about variational inference here? So we've seen there is a close relation between the measures and the correlations in the estimated means. That is, the higher the correlation, the higher are the measures. And the question is that trivial? So, because in the update rule, we have seen that we do take into account the covariance of the target distribution, so it's maybe no surprise. But at the same time, the approximative variational distribution is still mean field. But we can ask, is this still trivial? We don't know, so that's what Miguel and I are currently thinking about. Then it seems for suboptimal inference that the synergistic contributions decrease for very high correlated target distributions. We have quite some counterintuitive effects in double redundancy. And it's very important to bear in mind that this is a super minimal setup. So it's an open question how results generalize. Okay, what do we learn about emergence and complexity? So what do we gain from using those measures versus simpler ones, for instance, total correlation? So in this application, as well as in other ones that I've been having a look at, emergence and complexity, so measures of emergence and complexity, often don't tell us that much more than simpler measures of correlation. If we use no candidate macro variable, and if we do use one, so there are measures, and the Shannon-based whole parts emergence is part of those, where we do need to have a candidate emergent macro variable. We can get supportive results, but quite some variability as well. Then the question arises, to what extent we can use those measures to get support for something interesting going on. And I think there's quite a high risk of having false positives, because if the measures score high, actually just correlation may be going on. And quite a few people have the hope that those measures can be used to detect emergent macro variables without any a priori knowledge. I think this is, I'm personally skeptical about it. I think if at all, we can use those measures to corroborate, but probably not refute hypotheses about emergent macro variables. And so overall, yeah, I think we need more sophisticated testing and benchmarking procedures. But then we do have a very fundamental problem, which is the problem of engineering emergence. So the systematic modeling of emergence. And with that, I want to end with a quote from Joachim Fromm, who says, "It is difficult to engineer a system which creates and makes its own laws. The problem in the engineering of many complex systems is emergence. Does the combination of engineering and emergence make sense? Can we design a predictable system with unpredictable properties, or is it a contradiction in itself? The central question mentioned above is also the core problem of science in general. to find simple rules for complex patterns, to uncover simple laws behind complex behaviors, and to discover simple theories for complex phenomena. So with that, I want to thank you, and I also want to thank my collaborators, supervisors, and everyone else who has impacted my research.